Okay, yeah. So yeah, thank you all for attending AI for Weather and Climate 2. So yeah, I guess we may as well get started. So actually the first talk is an unsupervised machine learning algorithm for the identification and tracking of Lagrangian mesoscale eddies. And we have Anass Aouni giving this talk. Okay, yeah, we can see the slides. Thank you.
All right, perfect. Hello, everyone. My name is Anass Aouni, and I work for NCAI in France. And I'll be presenting for you some results about the automatic detection and tracking of Lagrangian eddies, which I will start first by motivating it and putting it in the context. Then I'll proceed to briefly explain the method and show a few examples of applications. So during the last decade, more ocean data has been collected compared to all the previous ones combined, leading to what we know by the ocean big data. So from one side, there are a lot of valuable information hidden in this huge amount of data, but on the other side, this makes their processing and modeling very complicated. So now more than ever, there is a need to establish a solid foundation for processing this huge amount of data with the goal of retrieving and synthesizing the most pertinent information for applications of great environmental, social, and ecological importance. And to succeed in doing this, one way is to focus on the concept of coherent object, and more precisely, material object called Lagrangian coherent structures, which actually can be defined as material surfaces that live long enough to be observed. And here I share with you some pictures displaying different types of LCS that can be found in the ocean atmosphere. For example, the first image shows a coherent jet over an SST image on the Gulf Stream. Then we have a tornado over sea. And here we have a mesoscale eddy trapping plankton in the Southern Ocean. And finally, a steam ring of a volcano. So as I said, the LCS are the most influential part of fluid flow. Therefore, their dynamics play an important role at different levels. For example, at the climate level, they control the distribution of water properties. They are behind different processes and phenomena. For example, they modulate the energy and momentum. They maintain the extratropical climate, and also they control the air-sea interactions. The LCS also play important role at the ecological level. For example, they control the distribution of plankton community, but also influence the behavior and displacement of fish and top marine predator. Therefore, they constitute a solid basis to develop ecological approach for fishery management and for marine life modeling in general. And finally, they also play a very important role at the environmental level. So the LCS will allow us to predict the evolution of marine or atmospheric contamination or pollution, for example, oil spill, or even natural phenomena such as the algal bloom, and will allow us to take decisions in advance. So here in this presentation, I'll be talking exactly about specific type of the LCS, which are known by mesoscale eddies or Lagrangian mesoscale eddies. So these physical structures are actually omnipresent in the ocean and can have huge impact on it. Some of them are known by stirring and mixing surrounding water, and others are known by their ability to trap and carry fluid flow in a coherent manner. So here we are actually interested in the second type, which are characterized by lifetime of weeks and months and diameters of hundreds of kilometers. And they're also known by trapping different water properties such as the salinity, heat, and plankton, and transfer it from one area to another. And because of their importance, several methods actually have been proposed in the literature together with automatic tools to their detection. Most of these methods actually take place in the Eulerian perspective, which make use of instantaneous velocity field to detect their boundaries. But by not following the fluid flow, these methods miss a huge part of the coherency of their detected eddies. For example, here I show eddies or boundary of eddies that were extracted by an Eulerian method. which I will advect with the flow for a certain period of time. And you can see none of these eddies actually maintain their coherency, but rather they all fold and filament everywhere. On the other hand, the Lagrangian perspective actually is powerful because it follows fluid flow, and therefore it gives more insight into their dynamics. So several methods actually have been proposed within this perspective, which fall into two classes, probabilistic and geometric. And all together, they form what we know by the LCS concept, or Lagrangian coherence structure concept. So this concept as it is today, it is based on the solving of a differential equation of the velocity field, from which we defined what we know by the flow map, which is a map which associates each particle at an initial time t0 and its position at a given time t. And the easiest way in which actually I can explain this concept is the following. This concept is based on the mapping of different Lagrangian properties into a scalar field from which we look for coherent structures according to different criteria. For example, the criteria could be an homogeneous region of the relative vorticity or the vorticity deviation or even trajectory frequency. So this philosophy, the philosophy of this concept gave birth to different methods between the year of 2000 and the year of the foundation of this concept until nowadays. However, despite all these developments and despite their broadly recognized significance, this concept suffers from a functional viewpoint. It is only capable of detecting the structures which are coherent at the initial time and maintain their coherency until the final time. So this concept has no idea on what's going on in between. And secondly, it is computationally very costly, which make their operational functioning not possible for now. So here in this work, I will present for you briefly a new hybrid method, which makes it actually possible to solve the aforementioned issues. So the method here we propose actually is hybrid, and it makes use of geometrical properties of the velocity field and the unsupervised clustering algorithm. So the procedure starts by segmenting Lagrangian trajectories into rotational segments based on the geometrical properties of their evolving velocity. So particularly, it looks for loopy trajectories, which are signs of material rotation. Then it maps the initial and final position of the structural rotational segments into a time-evolving grid. Then it uses a grid density algorithm to group them into different classes characterized by different transport properties, which represent the core, the coherent core of the eddies. Then we define an eddy, E, as a time-evolving domain, E, in a way that E is a set of adjacent particles characterized by rotational segment that coexists in the dense region at the initial and at the final time. And now I pass to carry on some experiments, and more particularly to highlight the computational aspect of the proposed method. So here we decided to detect all the mesoscale eddies of the Canary Current during the year of 2006 using our method and a recent method that is developed within the concept of DLCS. So the first method, which is developed within the concept of DLCS, takes around 2 hours in total. Meanwhile, our method takes only 3 minutes in total, which is actually 40 times faster. And just for the recall, both simulations were actually done in a normal computer, which is i7 core. And also to highlight the high monitoring ability of our method, we applied both methods on a numerical simulation of fluid flow with 3 eddies characterized by different relative vorticity. The first method, which is developed within the concept of the LCS, detects only 1 eddy. Meanwhile, our method detected all the eddies from birth to death, showing actually high monitoring capacity. So to summarize, here we propose a novel method to identify and track eddies in an automatic manner. The method actually is scalar-free and makes it possible to overcome the functionality issues of the LCS concept, which are when, where, and how the coherency emerged, and especially with the low computational cost. And in the future, we would like to advance the proposed method to include several coevolving quantities such as the temperature, chlorophyll, chemical pollution, etc., etc. And finally, we would like to advance the method to support real-time tracking of these physical structures. And for more details about the method, you can actually check my recent paper published in Journal Physics of Fluid, and feel free to contact me. Thank you.
Yeah, so thank you very much for that. Yeah, we have actually a fair amount of time for questions. I don't see any in the chat yet. I must admit, I don't recall if we're allowing for oral questions, but
just as a quick reminder that the chat isn't enabled here because we're routing all questions through the Slack channel. So we've pasted it in there a couple times, but there is a Slack channel that is a 03 weather and climate. So if you do have questions, please add them there.
Yes, and yeah, this is actually one also that will be monitored, so you can ask questions later, or if there are questions that involve more detailed replies, then Anass or later on others can get back to you as well.
All right. Andrew, should we pass it over to Andrew?
Oh, actually, one thing. Christina has a question, actually, asking if there are issues in overtraining due to how long a particular eddy persists.
Here, there is no training because it's an unsupervised method. It is only based on geometrical properties of the Lagrangian velocities and later on a clustering algorithm, which is unsupervised. So there is no training procedure.
Oh, okay. Yeah, and actually, I think that brings that brings another question. So, like, I noticed your abstract did mention that in the method that you're able to describe, say, splitting and vanishing.
Vanishing, that's right.
Is your method, either by itself or maybe coming up in the future, is it able to gosh, what's a good way to ask, to actually properly represent that this was, let's say, one eddy that then did split into two, and then I imagine it's possible even for those to merge to others. And so you can imagine coming up with something like a graph structure that describes the spawning, or essentially the splitting of eddies and merging and disappearance and the like.
That's actually a good question. As it is for now, it is not actually capable of detecting the splitting and later on the merging again. It only like follow one eddy. If it splits to two, it's only considered as one. As for now, it is not possible for the method. Maybe later on we work on that.
Oh, okay. Okay, yeah, thank you for that.
Okay.
And yeah, there actually there is also a question from Shruti asking that how did you decide on which unsupervised clustering, presumably which unsupervised clustering method to use, and were there differences in performance?
Well, the only one was actually available in the table is the grid density, because we're using a regular grid and actually dealing with positions of particles. So we didn't have enough options.
Okay. All right. Yeah. Thank you.
You're welcome.
So yeah, I guess it.
Go ahead, Nikunj. Sorry.
Yeah. I think maybe. Oh no, I was actually going to answer your question from a fair amount earlier, where perhaps it is reasonable to move to Andrews.
All right, and I believe that Jordan, are you going to be able to share your screen? So.
Yep.
And drive Andrew's slides. All right, great.
Yeah, I believe so. So Andrew, just give me a cue as you're ready for me to transition to the next one.
Okay. Yep.
And let me toggle back so I can mute here real quick.
Looks good, Jordan. Andrew, whenever you're ready.
Yeah. Okay. Yeah. So this work was looking at we're developing machine learning precipitation products within the MRMS group, and specifically for this project, it was looking at complex terrain and how maybe an ML method could do in that type of scenario. So I listed the collaborators all from the MRMS group that I worked on this project with. And yeah, next slide. Yeah, so this is just a broad overview of the method. So we decided that a CNN would probably be the best approach for this type of precipitation estimation problem. So the way it works is we've got a 5x5 grid of different input variables. So we tested out radar, model, and terrain related. And the way it works is it takes those 5x5 grids, goes through the whole, all the model layers you see on the right-hand side, and at the end it comes up with an output at the central grid point, and that output is an hourly precipitation amount. And the way we train it, for the truth data set, we used a couple of different data sets. First, we used the hourly gauge amounts from a data set of gauges as the truth to train against. And then later on in the work, we incorporated actually a gridded multi-sensor QPE as part of the truth data set. And so we went ahead and applied this model to a couple different domains, one domain over California, and then another one over Hawaii. In both these areas, they have a lot of mountainous terrain, and so they tend to be affected by orographically enhanced precipitation quite a bit. MRMS radar-based QPEs don't do as well in those scenarios, representing the microphysical processes of the orographic enhancement. And so we wanted to see if the machine learning model could improve a bit on that. Next slide. Yeah, so this is looking at all the input variables that we tested throughout the process. So on the left is all the radar variables we looked at. It ended up being that the one listed at the top of that left column, the seamless hybrid scan reflectivity, was actually the one that was kind of the most important to the model, the one that the model keyed on for its predictions. So we found that, and then the other two columns were the variables we attempted to put into the training for the model. So we tried several different model variables, and then some other terrain-related variables that we thought would help the model, especially in predicting scenarios of orographic lift. And so these included things like the mean wind and terrain height and slope, several different parameters like that. And then for the model variables, we tried things like precipitable water and several different parameters there. Next slide. So yeah, we went through a lot of pre-processing steps before running the model. So one thing to note is we split the data into precipitation bins. So once we did that, we then sampled evenly across each bin, so that you would have the same number of samples and you would avoid the model kind of being biased towards the really low end precip amounts, because those would have a lot more or a lot more samples if we didn't do this undersampling approach. And then for data augmentation, we ended up applying a rotation, 3 different rotations to each input field, and that gave us 3 times as much as many samples, and just making the data set more robust for the model to train off of. Next slide. So just getting into the cases and some of the results we found. So this was an atmospheric river event from 2019, and you can see on the right was the MRMS radar-based product that was run operationally at this time. And what you're looking at here is the QPE, and then overlaid these circles represent 24-hour CocoRa's gauge values. And so the darker reds correspond to underestimates from the QPE relative to the CocoRa's gauges. And then as you get into lighter colors, that's a better match between gauge and QPE. And then as you get into the darker blues, that's representing an overestimate. So you can see for this case on the right-hand image, there's just a pretty large underestimate bias from the operational product, seen both in the scatter plot, and you can see on the actual figure. And then to the left is the CNN model output for this same event for 24-hour accumulation compared to CocoRa's, and you can see that the statistics look quite a bit better. The scatter plot seems to follow the 1-to-1 line a bit. It's brought up those underestimates. And one interesting finding we had, or kind of a nice result, was if you look in Northern California for the image on the right, there's a lot of underestimates, especially in kind of this area where you're between 3 different radars. And so the radar-based approach is kind of struggling there to see what the actual low-level precipitation could be, because their radar beams are pretty high up. So on the left, if you look at that same area, the CNN has filled it in pretty nicely using the other variables that it has to use to make the prediction. So that was encouraging result there. Next slide. Next slide. Oh, sorry, can you go back one? I think I missed it, yeah. This was another event. Again, on the right, you have a lot of underestimates from the operational radar-based product. And then when you look on the left with the CNN output, it does get rid of a lot of that underestimate bias. It does have, in the scatter plot, you see a bit more spread than we would like. And if you look in the actual figure, there's a lot of overestimates that have been introduced. And so I kind of zoom in on one of these areas of overestimation in the next slide. So yeah, go on to next slide. Yeah, so in this area of Southern Oregon, we had a lot of overestimates from the CNN. And I looked at the precipitation type, and it ended up that most of this area was frozen precip. It was mostly snow. And so that kind of indicated that maybe the model doesn't do as well in frozen compared to just plain rain. So I tried explicitly adding the precipitation type as an input variable to the model. And on the next slide, I show, this is without the precipitation type. And then if you kind of scroll forward, you can see there's a difference, a bit of a tightening of the scatter plot about the 1-to-1 line. There seems to be some signal that including this variable is important. But I think what we want to do in the future is just include more events that are having frozen precipitation in the training data set to allow the model to maybe do even better with these types of events. Next slide. So this, yeah, I'll just go quick through this one. It kind of just shows a similar on the right, underestimates from the radar-based product, and then on the left, some improvement from the CNN, but this was one that where it didn't do so good. I mean, there's a decent amount of spread and some overestimate bias introduced. And then next slide. So this is just the final case I'll show. And you had, again, a lot of underestimates from the MRMS radar-based product on the right, and then on the left, the CNN kind of does a bit better with the biases, but it does have some remaining underestimate bias, especially if you look in Southern California in a pretty light precip area. It's having a lot of underestimate bias there. And on the next slide, I took a look at that. So next slide. Yeah, so this was, again, looking at what was causing the underestimate bias. I looked at the height of that lowest radar observation, and it looked like in this area, it was pretty high up. The lowest beam observations were pretty high up, like 2 to 3 kilometers in a lot of areas where there was there's mountainous areas interspersed in this region. And so it looks like the beam was probably overshooting some echoes, which if it's overshooting completely, the model doesn't really have much in terms of radar variables to go off of. Or if it does have some information, it's pretty high up and the model's not correcting it properly down to the ground in this scenario. So maybe feeding more light precip type training examples we think would help, again, with this type of event. Next slide. And then I'll just go real quick through, we ran the same CNN model for Hawaii. On the right, we had a lot of underestimates from the radar-based product. On the left, it does look improved, especially over the Big Island of Hawaii. And then on the next slide, it's just, again, another case, similar types of results where we're seeing some improvements from the CNN also over the Hawaii domain. So
2 minutes, Andrew.
Yeah, next slide. Yeah, I'll just wrap up. It looks like we've, the CNN has a lot of potential, it seems like, in these types of complex terrain areas to provide some improvements over the current physically based products. There are some biases we've identified in ways where we can kind of tweak the model to, we think, maybe improve that. But overall, we just want a longer term statistical analysis to get a really better idea of how the model performs over a more robust data set, and that could kind of lead into eventual deployment in real time of this type of technique. So that's all I had for today.
So yeah, thank you, Andrew. So yeah, there are more questions in the chat than what we will have time to deal with here. But I could manage to read off one question, which is that what was the form of your input of precipitation type within the model?
It just comes from our MRMS precipitation type product that we generate. So yeah, it's just kind of
like, was it in the form of like a one-hot encoding or?
Yeah, it's just we're just passing different numbers corresponding to the different precipitation types. So it's not one hot encoding. It's just a number corresponds to a precipitation type, and each point has a different number, or may have the same number if it's the same precipitation type. But
Oh, okay.
Yeah.
Is there a natural ordering in those then? Like, otherwise
Yeah.
you get that problem of, right, if you have numbers like 1, 2, and 3 representing different types, but there's no natural ordering, you could come up with a relationship that's spurious.
Right. Yeah, I haven't taken that into account yet, but yeah, I don't think there's really a natural ordering to the numbers at this point.
Okay, I understand. Thank you. Yeah, please do also check the chat because yeah, there are several other questions, but we won't have time to deal with them here. But yeah, thank you very much for that talk, Andrew.
Right. Thanks.
Thank you. And yeah, I guess we can have Ignacio Lopez-Gomez.
Yeah. I can share my screen.
Telling us about the predicting extreme heat.
Yeah, okay. So hello, everyone. My name is Ignacio. I'm going to be talking about predicting extreme heat using artificial intelligence. And this is work done together with Amy McGovern and Jason Hickey at Google Research. So why do we care about extreme heat? Well, we care because heat waves are increasing in frequency, and this is a robust trend all over the world. They are increasing by a few days per decade everywhere since the 1950s or so. And this is important because, of course, heat waves have negative impacts on human society. These impacts include increased mortality in the summers, exemplified by the more than 70,000 excess deaths during the European heat wave of 2003. They also result in increased risk of wildfires, as we've seen here in the west coast of the US over the past couple of years, and also reduced yields of agricultural crops. So if we want to mitigate some of these impacts in the future, what we need are accurate prediction systems that remain accurate for more than just a few days of lead time, because we need enough time to implement effective mitigation strategies for these impacts. And so the problem is that current technology, or current best technology, which is based in numerical weather prediction models, they are skillful for a couple of days of lead time. And I'm exemplifying that with the figure on the right, which is from Wolf and Meissen in GRL. And we can see that these models, so there's 4 operational models compared to persistence, and these models have high predictive skill for the first few days of the first week, but that predictive skill falls off quite fast after the first week. And some models already struggle to do better than persistence in the second week. And so the question is, can we do better? Apart from improving numerical weather prediction models, can we do better with other methods, such as data-driven methods? In this context, Miller et al. Very recently showed that with just a simple linear regression model based on North Pacific SSTs and soil moisture, they can actually outperform one of these operational models after 14 days of lead time. So for lead times in the 3rd or the 4th week, they can actually outperform this with a linear regression model. And so building on this, what we wanted to do is explore the skill of neural networks to predict extreme heat on a global scale, which it has been done before for more localized problems, but we wanted to do this on a global scale. And we wanted to do this for daily to weekly timescales into the subseasonal timescale. In order to do this, the data that we use are fields from the ERA5 reanalysis product at 200-kilometer resolution. And for each prediction, we will be using data from the 3 previous days. Some of the fields that we use for the prediction are the temperature at 2 meters above the surface, or its climatological anomaly, the geopotential height at different pressure levels, particular 300, 500, and 700 hectopascals, soil moisture, outgoing long wave radiation, and some static auxiliary fields. And with these predictors, our target is to predict the daily average climatological anomaly of the temperature just above the surface for lead times from 1 to 14 days. That's what we're considering for now. In order to build an efficient model of this, we map the ERA5 reanalysis product data onto a mnemonic cube sphere, and we do so using software developed by Paul Ulrich and co-authors. Once the data is on the cube sphere, we are going to be building convolutional neural networks, and the convolutions that we use for this problem are based on previous work by Jonathan Wayne, published at James. And so what we do is basically 2D convolutions on each of the faces of the cube sphere. And we communicate the different faces of the cube sphere through halo exchange. So we can see that in the figure to the right next to the comic sketch, where in each convolution we can take information from the different faces and so communicate the predication on Earth with other locations. In order to tackle this problem, we implement some of the key characteristics of the forecast task into the model architecture. And so the first one, of course, this being an atmospheric flow related problem, is the multi-scale nature of the problem. Due to this, we use a UNet type of architecture. In particular, we base our model in the UNet 3+ architecture. And we use different resolutions varying from the finer resolution we consider of 200 kilometers all the way to the synoptic scale of 100 kilometers. Apart from this, we also want to capture teleconnections or long-range dependencies, especially because we're just using a convolutional architecture here, no recurrency. So we need to learn about things that are far away in the globe. And so for that, we implement exponentially growing dilated convolutions with model depth, such that any given point in the cube sphere on the output can actually learn functions of any other point in the cube sphere in the input space. Once we have the model and we train them, something interesting that we observe is that there are trade-offs in the training. And so here I'm showing the results. So I'm showing the root mean squared error in the 2-meter temperature anomaly for 2 tasks. The first one is just prediction of anomalies over land on the left, and the second one is anomalies over land, but only for those days that there was a heat wave or extreme heat. And this is measured by basically the temperature anomaly being above 2 standard deviations from the climatology. And so what we observe here, we're comparing against persistence, which is the black line, and climatology, the green line. And we observe that if we want to have a model that performs better in general than persistence and climatology, then we just have to train with a generic or general purpose loss, such as the mean squared error. And that is the model with the blue line on the left, which is performing better than the others. But we see that if we actually take this model and try to focus on the extreme value forecasting, this model is actually doing worse than persistence. And so what we observe here is that if we want to do better than persistence, if we want a model with predictive skill, we have to use custom losses that are emphasizing the extreme values. And so we did this by basically fine-tuning the model using a loss based on the mean squared error of the exponential of the targets. And this yielded a model that was better than the previous one, and of course also better than persistence. And that is the model that is shown in the orange line here. And we can see if we go back to the left figure, we can see that there's a price to pay in that model is actually doing worse than climatology for just the average prediction task. So that's important to take into account. Now, these results are just for prediction over land. Something very interesting that we also observe is that apart from doing better over land, our model does much better than persistence over the oceans. And so here I'm just showing the error of the persistence model on the left and the error of our model on the right for prediction tasks over the summers of 2017 and 2018. And we can see that the errors for the persistence model are really high over the oceans particularly, and our model performs similarly well over the oceans and over continents. So this is something important to take into account if we want a model that a model that we're going to use as time marching, because we would want to minimize errors everywhere, not only over land. And finally, here I'm just showing the results of our model for a particular case study. So in this case, we focused on the 2018 European heat wave. On the left, I'm just showing the magnitude of the temperature anomaly in standard deviations over climatology. And so the regions that don't have any color means that they were not above that threshold. So in terms of our definition. And then in the middle figure and to the right, I'm showing the root mean squared error of 2 models. The first one is persistence with prediction lead times of 7 days. And the one to the right is for the same forecasting task, our best trained model. And we can see that our best trained forecast model does better than persistence everywhere, and this difference is particularly important in coastal areas or over the ocean, as we saw before. The conclusions that we had from this study is that global convolutional neural networks, when performed on the cube sphere, can consistently outperform persistence in these forecasting tasks, so extreme heat prediction, for the lead times that we considered, that were from 1 to 14 days, and just using ERA5 reanalysis data. This problem has been studied before using synthetic data from climate models of thousands of years. And so we wanted to see if this was actually possible with the limited amount of data that we have from historical reanalysis. Another important point that we learned is that basically the use of fine-tuning with loss functions tailored to the extreme events, or that emphasize the extreme events, is crucial if you want to have a model that is better than persistence for all lead times. But that this actually makes the model do worse for the more average forecasting task. And so this is something that is important to take into account in the development of general purpose neural weather prediction systems that may also be used for extreme heat prediction. Of course, this is ongoing work, and some of the future directions that we'll be exploring are the implementation of some recurrent architectures and seeing if we can improve upon our results. And we want to consider longer lead times into the subseasonal timescale, so 3 to 4 weeks ahead. We want to compare to numerical weather prediction-based models. So far we've compared to persistence, but we want to compare to the operational models as well. And finally, we want to extend this model HeatNet to predict more relevant heat indices, not only temperature, such as the wet bulb temperature or their humidity-based markers as well. And with that, I'll take any questions.
Thank you, Ignacio. So yeah, we do have some questions in the chat. First one, Vikram asks whether the RMSE values that you show, are they training or test values? He's just wondering about overfitting.
Yeah, good question. So they are testing values, and we use for training, we use 1979 to 2012 from the historical reanalysis. Then we use 2013 to 2015 as validation, and we use 2016 onward as test. So there's an important gap of 2 years. So there's no time correlations between our training and our testing sets. Yeah, that's a good question.
Oh, okay, great. Yeah, and the next question is that how will the performance change if you use the original lat-long grid?
So that is also a good question. We didn't check the lat-long grid because just from experience in the group at Google Research, when using the same convolutional weights in the higher latitudes with a lat-long grid, it's difficult to learn about velocities because the distances are severely distorted, and so we expect that the results will be significantly worse for a global problem. But a lat-long grid might work for localized problems in the tropics or maybe moderate extratropics.
Oh, okay. Yeah, thank you very much. And yeah, apologies to the other questioners. We will have to leave it at that. But yeah, Ignacio, please do check the Slack channel there, the weather and climate one, because there are many more questions.
Okay, thank you.
So yeah, thank you for your talk. And yeah, I guess yeah, next we have Zhongrun Xiang talking about rainfall runoff modeling. I guess you're.
I'm here.
Hey, your screen came.
Yeah.
All right. Yeah, looks good.
Yeah, everyone can see my screen. Yeah. Okay.
Yeah.
Hi, my name is Zhongrun Xiang. I'm a PhD candidate from the University of Iowa. Today, I'm going to present my research topic about the fully distributed rainfall runoff modeling using the spatial-temporal graph neural network. Today, I'm going to talk about the problem definitions, data study area, model architecture, and how I set up the parameters, and also my results. So today, many of the deep learning models, they talked about the rainfall runoff modeling. They use lumped models, so they're assuming that each model is they're assuming that each like watershed, they consider each watershed as a point and consider the watershed scale rainfall runoff models. So in this way, so people considering the rainfall happen on the whole watershed as at each hour is one data. So sometimes, so when we have multiple observations, for example, we have the as we see the semi-distributed model here, if we have multiple USGS gauge observations, we can construct this model, one watershed into several sub-watersheds and develop one model for each sub-watershed. There are many papers talking about how we consider upstream downstream correlations. However, these all ignore the rainfall information that the rainfall distribution that are unequally inside of each watershed. If we consider semi-distribution like this, we still consider the whole part of the sub-watershed as a unit. This is not that accurate. So in my study, I'm thinking if we can develop a fully distributed model on the rainfall runoff problem. One way is to construct the unidirectional directed graph. We can use the flow direction data. So here is example. If we have a watershed look like this, and the yellow part is our watershed, so we have a watershed look like this, and our outflow is outlets here. We can construct simply on the convert it into a graph like this, right? So our output will be our final flow will be the F area. How can we model it? I'll talk about later. So I'm focused on a study area, which is a single large watershed. So we don't have any. We have only one USGS gauge on the southeast area. This is only one outlet. We have a USGS gauge there. This is over 1,300 square kilometers. It's large. We can convert it into like both ways, like directional D4 or D8. This is D4. This is D8. We can constructed our graph using several different ways. Also, we have the data for seven years. So 7 water years from October 2011 to September 2018. We split our data set into train, validation, and test 4 to 1 years. So we generate our DEM using our 90 meter grid, and however, the rainfall data we use is a 4 kilometer stage 4 multi-sensor measurement. In this way, as we show here, the grid here is a 4 kilometer times 4 kilometer square. So this is how we constructed our rainfall data. We have the rainfall data from NOAA is in 4 kilometer. We only have one observation from USGS. This is a point. We have only point. So let me see how we make this using a graph neural net. What is a graph neural network? Simply, we can consider two different steps. First is to average message from its neighbors. Second, then we apply a neural network. For example, if our target node is A here, we just calculate its neighbors. Who goes to the A? It is B, C, and D, and then who goes to B? Is C here, and it is B. It is the E. It is the F. So this is how a graph neural net will work. So we sample the different hop. We call the K-hop neighbors. So 1 hop neighbor, 2 hop neighbor, and then we connect it. So in this way, I designed a graph neural network based using sequence models. First step, we want to here we show here example to remind what is going to happen. So first step, we want to have the rainfall runoff on the land. For example, on this land, on each land, we are going to have our rainfall runoff model because the rainfall happens on this land. Each of them need a time series rainfall runoff model. So this is going to convert from rainfall to runoff. How many runoff we generate on this land? So for example, it's the same example here. We have 8 lands here. We convert it into the graph first, and then on this graph we have 8 nodes. 8 nodes here. Each node represents a land, and we use a rainfall runoff model. We call it a temporal model, and then we aggregate them. For example, this is our output. This is our final output, and it has 3 connections to it. For example, F here, it has three connections to it. So we aggregate these three of them. Simply, I'm using the sum up function in my models, so to aggregate them, because these three area, they have water flow to our final output. Then we have this is called level 1 or 1 hop neighbor, and this is a 2 hop neighbor, and we have 3 hop neighbor. So in this case, we have only 3 hop neighbors. In the end, we aggregate from 8 nodes to 4 nodes. We have 1, 2, 3, 4. So this represents the directions in somewhat ways. Here we assume that each 4 kilometer grid represents the same distance. In this way, we are assuming that yes, we have another sequence model. We need to do the space-time confluence. So we need a spatial model to deal with it. The same thing, we can use a sequence model to work on it. This is our final output. This is the 1 hop neighbor, it takes time. And then 3 hop neighborhood, it takes the same time as well. And we create another sequence model. In this way, we need to, how many layers we need. The first thing is for the rainfall runoff, we call it temporal model. On the land, we only need 1 model, which means 8 different, I marked red T here, they share the same model. As I published as a preprint before, we can develop original model that using the deep learning, which means we include the land, we include the geospatial information. For example, the land area, the land soil types, the land soil cover, and the like all the information if you have to make this generalized model. So here we have 8 nodes. Each of them share the same parameters. So we have 1 model. We call this 1 sequence model for rainfall runoff on the land. And then we use and this is multi-step. And then we create a sequence model for the spatial level. So what type of sequence model am I using?
Sorry, Zhongrun, you have about 4 minutes left.
Yeah. So how many parameters I'm going to have? First is LSTM. This is one of the most known information, and the layer people are using for time series modeling. Another is temporal convolutional network. This is another famous model we are using here. So for the time series, because what I propose is graph network. This is this is just a structure, so we can use either LSTM or bidirectional LSTM, gated temporal convolution network, or bidirectional gated temporal convolution. Each of them works. So I'm assuming we have a 72-hour window for the path to predict the next 1 hour runoff. So for the temporal one, we can use either of them, and the same thing for the spatial one, we can use either of these 4 models as well. Here we have 8 different settings because we can use D4 and D8 to generate our flow direction. In the end, as we can see here, the preview here shows how spatial information is important. In some cases, we have the lag time between rainfall and runoff is like 6 to 8 hours, and sometimes it's only like 2 hours. This is because the spatial distribution is very important. And here I show the results using I named it graph neural rainfall runoff model. As we can see, my model shows the best result. Some is D4, some is D8. It shows the best results no matter on KGE or NSE or root mean square error. It is always the best compared to simple lumped model or using CNN-based model. Here is a case like the result just show a case that what happens, and we can see even in a very complicated case, our graph neural rainfall runoff model is also the best. That's it. Thank you very much.
Yeah, thank you very much for that talk. One question I have, if I may,
Yep.
you mentioned, let's suppose you have enough information to set up something semi-distributed, right? Like you have a general idea of what the structure is, the water flow overall. Yeah. Is there a way in your method now, or maybe in the future, where you can imagine putting that as an initial input and then having the model refine itself?
In my current way, I will construct it into like two different parts. The first is fully distributed for the rainfall data, and then we have a semi-distributed model for the stream flow or runoff data, and then we combine them together. Yeah.
Okay. Yeah.
Yeah. If our goal is our final output, yeah, it will be, yeah, we can combine two different models together. Yeah.
Yeah. That sounds good. Yeah. Thank you very much.
Yeah.
So yeah, good timing here. We have next Christina Kumler talking about random forest fire radiative power model.
All right, I am going to share my screen and trust that you all can see it because I can no longer see you. So this talk.
Hey, yep, it looks good, full screen mode and all. Please have at it. Thanks.
So this talk is about improving wildfire, double fire, radiative power estimates with random forest. And this work was done in collaboration with Ravon. You might recognize his name from a lot of work with the HER smoke model, and then Jeb Stewart. So I would like to start with our motivation. How is FRP, fire radiative power, derived for modeling purposes right now? What are satellites currently capable of deriving? And what are some potential societal impacts of improving how we model FRP in numerical weather models? So currently, her group takes a mean daily FRP, so the average of FRP over a day, and then multiplies it by some amplitude depending upon if it's a wildfire or a controlled fire on this Gaussian curve that you can see in this image, to then represent some hourly FRP value during a forecast period. So that's a lot to digest. They take the mean daily FRP from the day before, and then they multiply that value by whatever hour of the day it is in UTC, and then that produces their current FRP value. Now, for satellite derivations, you have your polar satellites as well as your geostationary satellites, and they work on different resolutions as well as different temporal timescales. So the geostationary satellites have a lower resolution, so they cover a larger grid, but they take hourly snapshots, and from those bands, an FRP value is derived for a certain grid cell. Polar satellites have a much higher resolution, but they only make a pass over a certain fire or area a set number times of days, which can range from 4, 6, or 8 times. Now, a caveat in deriving FRP from satellites is that sometimes, as you can see in this lower image, both clouds and the actual fire plume can block out derivations of an FRP value at its perimeter area. So you might not capture the whole FRP of a fire because certain areas are blocked out in that particular satellite image. So this modeling of FRP and improving how we model FRP in something like the HER smoke model would greatly help us in situations where we might not always be able to derive an FRP value from a satellite image at a given hour. This slide I created last year because last year the West and Colorado in particular really endured some intense fires, and really nails home how important it is to be better at representing and modeling these wildfires, both before when they happen, as well as when they are currently happening. And you can see from these giant smoke plumes in some of these images that wildfires, when burning very strong and intensely, can transport these aerosols for miles and miles and miles. This centered image, the smoke plume stretched nearly to Kansas for this particular fire. So some background into how we set up making these random forest models to derive FRP. We'll look at the different data inputs. I'll briefly talk about the models that I tried and didn't go with, and then we'll describe how I set up the project. So a couple years ago when I started this work, I looked at different types of machine learning models and didn't refine any of them, but upon just initial tests, found that the random forest model worked as well, if not the best, when comparing it to other models such as neural networks. And given the slightly more simplistic setup of a random forest, as well as the easier transparency in describing things such as importance of which variables you put into the model, we decided to stick with the random forest model. If you're unfamiliar with the random forest model, you specify a number of trees and ensembles in depth in your forest, and it kind of works to derive an answer by the best option of voting. In this particular image is a random forest with 10 trees allowed to go to a maximum depth of 3. So for our different experiments in the random forest, we had different types of data inputs. Some inputs that were consistent across the board. We had an hourly wind gust variable from RAP. We had the hourly temperature from
Nikunj, do you have audio? Just checking.
Oh, God, I was going to ask if it's just me, but yeah, no, it looks like
but
conked
you
out.
got her back. Christina.
Oh, am I here?
Yeah, we lost your audio for a bit. You might want to turn your camera off just to maybe improve your signal.
I can do that. I apologize.
No, we were hearing you perfectly, and then all of a sudden it just dropped. And so I think everyone was like, "Is that me?" Or
oh no. Okay, so I'm not sure where I cut out, but I will continue with the inputs.
Awesome.
So I included these RAP inputs, and the ones with the asterisks, if you didn't hear, are ones that I experimented with and found not to be as important inputs. And sometimes they even slightly produced worse performing models. So we chose to remove them from the future refined models. We also included longitude and hour of day. This is important because wildfires tend to happen more in the Western United States, and FRP values tend to be greater during the afternoon and early evenings. So both longitude and hour of day were included. Now, variable inputs were satellite FRP. So we have two different types of satellites, the geostationary, so GOES, and our polar orbiters. And these had to be treated uniquely because they work on different resolutions. So for a polar orbiter on a RAP domain, it might have multiple inputs. And if that's the case, then you aggregate or add up all of the FRP measurements for the one RAP domain, and that's your FRP value. But because GOES works on a larger domain, which is more close to the RAP domain, which is what we train the random forest on, then we tended to take an average if there were multiple GOES FRP measurements per grid cell. And we also experimented using the mean FRP value from the day before, which is how it's used now as an input, as well as a 24-hour rolling average, which produced better models. But given that that's not what's calculated right now, we can't use that random forest. And then I also experimented just using the hour before FRP value. So it became kind of like a persistence model. This is just kind of what your FRP looks like skewed across the CONUS for 2018. And the more extreme FRP values, so the higher FRP values, tend to be congregated more on the Western CONUS. This is kind of a statistical analysis looking at the FRP plotted against all of our input variables. I won't linger too long on this, but I did do some correlation testing on it and didn't find anything terribly high. Some of our highest values were 0.2, 0.1. And then when I did do the entire CONUS, I found that there was substantial correlation with longitude, but again, that makes sense based on how fires are distributed, and we're really emphasizing on wildfire FRP measurements, not something like a controlled burn. And then this is that relationship I was discussing with FRP given the hour of day. You can see that there is this daily cycle in FRP magnitude. So let's dive into the random forest models where we look at the inputs and the models. So we're remembering the inputs. Now I decided, in addition to splitting random forest models by the satellite input, we also would look at an entire CONUS trained random forest, as well as just a Western trained random forest that would look at any of the longitudes at or west of 105 west. Here is a model with result with 1,000 decision trees where it's run 42 times for an ensemble. And I inserted what the Python code looks like. It's very clean, it's very short. If you're looking to introduce yourself to machine learning methods in a random forest, might be a good model for you. I would suggest starting with it because it's fairly simple to understand. And this is what the spread for a CONUS trained model using GOES satellite FRP values look like. We have the predicted FRP on the left, and then the truth FRP or the GOES satellite FRP on the bottom.
About 4 minutes, Christina.
Mm-hmm. So here is another result, training a random forest off of polar satellite data just on the western portion of CONUS with the conditional that the mean FRP from the day before had to be greater than 0. So we're only looking at wrap domain grid cells where the FRP the day before was greater than 0. And this is to really help isolate these wildfire cases. This produced over 2018 a total of roughly 26,000 training samples and 11,000 testing samples. And the testing results for mean absolute error for this random forest was about 242. And that seems really high, but when you look at the spread of the FRP magnitudes, that they can push up to 1,000. And when you look at the MAE for the current method, it was 388. So it is an improvement. And then to the upper, my right, you can see each of my 7 variable inputs and how their importance broke down. So obviously the information about the FRP from the day before is the most important. And then the model looked at wind gust, temperature, and relative humidity to be the next important inputs. And then hour of day still had an importance greater than 0, but was the least important in these 7 inputs. Here is a plot of the spread of the random forest FRPs compared to the Gaussian FRPs. And one thing that I noticed from this plot is that the random forest had a lot narrower spread to the actual, compared to the actual Gaussian method. So for the sake of time, I'm going to jump just a little. This is another emphasis on that random forest really doing a better job at not being as wildly wrong in either direction, unlike the current Gaussian method. So this is a case study from the Williams Flat Fire in California in 2019. All of my data were trained and tested on 2018, so this is completely blind data. The red lines that you see here are the mean FRP values for that day. The FRP from GOES satellite is represented by these green lines, and then the random forest is represented by this blue. So you can see that the random forest is decently fit to the trend of the mean FRP value because it was an input. But when you look at it compared to the HER method, you can see that it is much more in control than the HER method, which sometimes predicted FRP to be up much higher than the mean FRP, as well as much higher than the actual GOES satellite. I would like to linger and finish with this case study. This is the Pine Gulch fire from Colorado last year. And again, this is completely blind tested data, so data that wasn't used in training or testing. And the HERS Gaussian MAE was about 640 for the entire duration of this fire, whereas the random forest was 246. So the random forest tremendously improves upon the existing method. Now, there's one caveat, is that I don't have the specific satellite measurements just quite yet to compare hour by hour. So these are compared to the mean FRP value. And then this is just another image to show how much of an improvement the random forest or the machine learning model is upon the HER. My last slide is on our current work. We are currently expanding our data set to train on 2018 and 2019 wildfires. We have highly quality controlled GOES data that we can train on from the summer of 2019. So even though it wasn't a huge wildfire season, we have super quality controlled data. So no solar flares from solar panels or anything like that. And we're also introducing 2 new RAP variables into the training data set. And if it works better, then we will update the current existing random forest. And that'll do.
Yeah, thank you very much, Christina. And yeah, sorry that the network took offense to you talking about wildfires at some point, I guess. But yeah, thanks so much. And we now have Kate Duffy telling us about land surface temperature. And yeah, Jordan, I think you were going to present this one or show the slides.
And Kate, how's your audio coming through? Kate was a little worried about her connection today.
Can you hear me now?
Yep, we can hear you, no problem. Jordan hasn't put your slides up yet, but I'm guessing he's working on it. All right.
Something's happening.
Looks good.
Great. Thank you, Jordan. Thanks so much. Hi, everyone. My name is Kate Duffy, and I will be presenting a generalizable machine learning approach for predicting land surface temperature. This project is in collaboration with my colleagues at the NASA Ames Research Center and the Bay Area Environmental Research Institute. Next slide, please. Land surface temperature is the skin temperature to touch of the topmost layer of the Earth that's visible from a satellite. And land surface temperature is unique from many other parameters from remote sensing in that it exhibits strong diurnal variability and the dynamics of daily temperature changes, such as the timing of peak temperature and the diurnal range between the low and high temperature, vary considerably across locations and seasons. Land surface temperature is the key parameter in surface and energy processes, surface energy and water processes from the local through global scales. And it's also a high priority observable for a variety of different scientific fields, including hydrology, agriculture, human health and urban environments, and looking at forest fire risk. Next slide, please. Satellite-derived products like land surface temperature are critical for detecting global change, including changes in the surface energy balance that have modified diurnal temperature cycling and extremes. Traditionally, most data products are generated from low Earth orbit or LEO sensors. As Christina just discussed before me, these data sets have global coverage and relatively long historical records, as well as potentially high spatial resolution due to a low orbit altitude. However, LEO sensors have limited temporal resolution of observations due to their orbit characteristics, and as a result, they cannot capture diurnal changes in surface conditions. Geostationary or geosensors are able to provide high temporal resolution observations with a large extent in space, which can better capture the diurnal variability of some key observables. And while these sensors have traditionally been used for weather observation, they have emerging applications for science due to their relative similarity to LEO sensors in terms of their spatial and spectral characteristics. However, they have the advantage that they can provide observations every 10 to 15 minutes. And these near continuous kind of observations have applications for monitoring processes that evolve rapidly in time, and also this helps to mitigate issues with cloud cover. Next slide, please. GOES-16 provides images that have a temporal frequency of 10 minutes in 16 different bands with spatial resolutions between 0.5 kilometer and 2 kilometers. These bands include the requisite thermal bands for estimating skin temperature. So therefore, GOES-16 has sufficient information to produce a 2 kilometer land surface temperature product every 10 minutes. In contrast, LEO sensors like MODIS and EcoStress have very well calibrated LST products, but with a time step of daily or longer. And due to the similar bands between the different sensors, but non-identical, it takes significant effort to transfer the physics-based models developed for LEO sensors to geosensors. So motivated by this challenge, we developed a deep learning-based method for LEO to geo algorithm emulation. Next slide, please. Our machine learning approach uses a convolutional neural network to learn a mapping between GOES level 1 data and MODIS land surface temperature. And this approach is based on the ability of neural networks to act as function approximators, and it takes advantage of the large volume of overlapping data products and observations that are available from different sensors. Our training pairs are built by matching overlapping observations of daily MODIS land surface temperature and GOES-16 bands. So we're exploiting these co-located and co-temporal observations from LEO and GEO satellites to test whether a neural network can act as a statistical model that can approximate the algorithm for LST retrieval. And once learned, this model can be applied to full disk images every 10 minutes to generate a hemispheric coverage of land surface temperature in near real time, whereas traditional methods generate results with coarsened spatial and temporal resolution. So the overall goal of the work is to develop a generalizable approach for predicting high quality, spatially and temporally consistent geophysical variables using data from geostationary sensors. Next slide, please. In our cross-sensor approach, we use the pair of LEO and GEO satellites, MODIS Terra and GOES-16. The inputs are geo-corrected level 1 geostationary products that were prepared by the Geostationary NASA Earth Exchange, the GeoNext project, and elevation is also used as a covariate. Our target for training is the MODIS Terra land surface temperature product, which is projected into the 2 kilometer level 1 grid used for the L1G data. And then matching in time is used to obtain quasi-simultaneous pairs of observations. We define a convolutional neural network in Python using PyTorch to approximate the split window algorithm, which shown here in the generalized form takes advantage of the differential absorption in consecutive thermal bands to estimate land surface temperature from radiance. Our network consists of 4 convolutional layers enclosed by 1 skip connection. And our model also handles cloud masking through a learned classifier, through which the model is conditioned to predict clear sky pixels using a compound objective function. For model assessment, the predictions are assessed by comparison with MODIS Terra LST over a holdout time period. The metrics include absolute fit, correlation, and the ability of the model to capture the observed distribution. Further, we test the generalization of the model against unseen times of day, which are observed by MODIS Aqua, and the application to another geostationary satellite, Himawari 8, which observes a completely separate geographic location from GOES 16. Next slide, please. So as I said, we trained the model to predict MODIS Terra LST from GOES 16 L1G's thermal bands using data from the year 2019, and then performed validation of the model by comparing inferences to Terra LST for the year 2020. And analysis of the model predictions indicates a good agreement between predicted LST and MODIS's LST product during 2020 with less than 2 Kelvin error and a correlation coefficient around 0.98. Plotting the geographic location of the errors reveals some spatial patterns. For example, the sign of the error exhibits a clustering in space, which may be related to some spatial variation in the land surface or atmospheric conditions, which I'm currently exploring explanations for. The model also achieves a cloud classification accuracy of about 95%. And this is an important task because it discriminates between the valid observations of the land surface and the cloud water body pixels in the relatively unprocessed level 1 data. Next slide, please. We further assessed the model by testing its generalization. We made predictions using level 1 data from a different geostationary satellite, Himawari 8, which is operated by the Japanese Meteorological Agency and observes the other side of the world. Himawari 8 sensor has similar thermal bands to the advanced baseline imager on GOES. Next slide, please. These density plots are used to assess the fit of the model under these different applications. Outlined in orange is application to the training sensors, MODIS, Terra, and GOES 16. To the top right, the trained model is applied to predict LST from the Himawari 8 multispectral data. And the prediction is compared against Terra LST, and a high association is maintained with an R value of 0.97. Additionally, we evaluated the performance of the model trained on MODIS Terra to predict land surface temperature at the time of day observed by MODIS Aqua. And the results indicate that the model generalizes to these other times of day. Next slide, please. And I will wrap up with a case study applying the model to observe a real-world heat event, which are events that increasingly affect us in the US and globally. We applied this model to look at a surface heat wave in California that took place in September of last year. The dots in black are hourly predictions of land surface temperature from our machine learning model at a point location in Death Valley, which happens to be the lowest point in the continental US and one of the hottest places on Earth. The MODIS Terra and Aqua observations are plotted as the hollow green and blue dots respectively. So you can assess the agreement and also see the diurnal dynamics that are visible when looking at hourly data. Several different studies have looked at metrics of surface heat in urban areas. So this illustrates one potentially impactful scientific use for high temporal resolution surface temperatures. Next slide, please. This is an animation that may or may not play of surface temperature predictions at a 10-minute time step for the Western US. Great. We can observe surface temperature dynamics as well as the movement of clouds. And data such as these can be generated in near real time using geostationary data feeds from GOES 16 and other satellites. Next slide, please. Thanks. So in conclusion, in this study, we demonstrated a data-driven method to predict land surface temperature from geostationary sensors by taking full advantage of overlapping data products and observations from LEO and geo sensors. Further, we looked at the applicability of the approach across unseen times of day, spatial regions, and sensors. The spatially and temporally consistent land surface temperature observations from geostationary satellites could be useful for understanding changes in the surface energy balance that are key climate change indicators. And using machine learning in this way can help leverage satellite data to address important science application questions. Last slide, please. That's all I have. Thank you all for listening.
Yeah, thank you, Kate, for the talk. And indeed, thanks to all the speakers for their presentations and to everyone who attended. Please note that the Slack channel here, which is the weather and climate one, will still be active after the session, so please feel free to ask questions there, and to all the speakers, please check there for questions that may be outstanding, and answer any questions that you can there. And yeah, also a reminder, thanks Jordan for posting this, that there will be there's a poster session this afternoon. Some really great video and static posters there, so please go and attend at the link that Jordan has provided in the chat associated with this Zoom. So yeah, that closes out this session. Thank you all.